Let's graph f of x equal x to the 2/3, practicing what we've just practiced on the previous problem with another problem, using this first and second derivative information that we're learning to use to produce graphs. So the first step is always to take the first derivative. So f prime of x is 2/3 x to the negative 1/3, which is 2/3 x to the 1/3. You could write that as 2/3 cube root of x. Then find the critical numbers, the numbers where the first derivative is 0 or where the first derivative is undefined. Let's actually look to see where the first derivative is undefined first, because that's easier on this one. We want to see where is 2/3 cube root of x not defined. Well, it's not defined at x equals 0 because this first derivative, if I let x be 0, then I'm dividing by 0. So you're basically looking for division by 0 here. What number do you put in for x to cause division by 0? Because the function that we're talking about, which in this case is the first derivative, would not be defined there. So this 0 is a critical number, and it's going to tell us where they're sharp corners or vertical tangents. Sharp corner would be like this or like this. A vertical tangent would be like that. Remember, the slope of a vertical line is undefined. So if the graph basically at a point gets almost vertical, in other words, at that point it is vertical, it still passes the vertical line test, but the tangent is vertical, then the derivative at this point is not defined. So at this point x equals 0, I know I've either got a corner or a cusp or something like this. You could also call this a corner or a vertical tangent. Don't know which. We'll figure it out from the rest of the pieces of the puzzle. Okay, where's the first derivative 0? That will tell us where they're horizontal tangents. So where, in other words, when I say where, I mean for what x? Where is 2/3 cube root of x equals 0? Well, for a fraction to be equal to 0, the top has to be 0, right? And the top is 2. So that tells us that there are no solutions here. There are no horizontal tangents. Another way to look at this is to multiply both sides by this denominator of 3 times the cube root of x. If you multiply the left-hand side by 3 times the cube root of x, you just get this 2. And you multiply the right-hand side, 0, by 3 times cube root of x, you get 0. So we get this false, absurd statement that 2 equals 0. That tells us that there are no critical numbers here. So there are no horizontal tangents. The graph never flattens out horizontally. Okay? Now, for any critical numbers, they're key numbers to have. They're important numbers to have. You need to see how high to plot those. 0 was a critical number. So we're going to find the y-coordinate. The y-coordinate would be 0 to the 2/3. Plug your critical number into your original function, and I get 0. So I know that 0, 0 is a point on my graph. Okay? And it's going to be an important number to have. Now, place critical numbers on the number line. Okay? have only one critical number, 0. What intervals on the number line result? They would be negative infinity to 0, and they would be 0 to infinity. Now, you pick a number in this interval, a number less than 0. How about negative 1? And you put that into the first derivative. The reason is that if the first derivative is positive, the function's increasing. If the first derivative is negative, the function's decreasing. It turns out that the behavior of this function is going to be the same throughout this interval, minus infinity to 0. And we would be another discussion to think about why that occurs. But we know that the function's either increasing throughout this whole interval, minus infinity to 0, or decreasing. And so we can just pick one number and see if it's increasing or decreasing at that number. And the behavior is going to be the same for every other number. Okay, so I put negative 1 into the first derivative. So let me come over to the side and work with that for a minute. It's 2 over 3 times the cube root of negative 1. The cube root of negative 1 is negative 1 because negative 1 cubed is negative 1. We're not talking about square root. That would be imaginary number. We're talking about cube root. We get negative 2/3. Don't care about whether it's negative 2/3, negative 3/4. All we care about is negative. The first derivative is negative throughout this interval from minus infinity to 0. So my function is decreasing throughout this interval. Go to my next interval, 0 to infinity. Pick a test value. Just pick a number in there. Say 1. I'm just picking an arbitrary number. Don't pick the endpoint, pick any other number. We'll put 1 into the first derivative. I get 2 over 3 times the cube root of 1. That's just 2/3. That's positive. So the function is increasing. Now I like to sketch a graph based on this first derivative information, putting these pieces of this puzzle that we have together. And then I'll see if I can't perfect the shape of the graph by doing the second derivative information. So what does the graph need to do? It needs to decrease on the interval minus infinity to 0. On this interval minus infinity to 0, it needs to decrease. So I start up high and decrease. And then from 0 to infinity, the graph needs to increase. I know my graph goes through this point, so I'll come up from this point. Now, what's happening at this point? Well, I don't have a horizontal tangent. It's not smooth like this. I've got what? A sharp corner, or something like this, or something like this. But I can't have this vertical tangent because that would say I was increasing throughout. And I've got to decrease and then increase. Okay? I don't think the graph is piecewise linear like this, because if that were the case, my function would have an exponent of 1 on x, okay? It's not got that. So I'm guessing the graph has to be something kind of like that. So that's what I'm going to draw. I've got the derivative here at 0 is not defined. It's decreasing on the interval minus infinity to 0, increasing from 0 to infinity. That meets the conditions above. Now, let's perfect the shape of the graph using the second derivative. What is the second derivative? I didn't leave much room, did I? Let's do this right here. The second derivative is 2/3 times negative 1/3 times x to the negative 4/3. So this is negative 2/9 over x to the 4/3, which is negative 2/9, the cube root of x to the 4th. Now notice the things that I do for the second derivative analysis are identical to things that I do for the first derivative analysis. I just don't necessarily call them the same thing. I want to see where the second derivative is undefined. I want to see where it's 0. That's exactly what I did up at the top when I was finding critical numbers. It's just that we don't call our results down here on the second derivative critical numbers. Critical numbers is a term that's restricted for first derivative. Okay, where's the second derivative undefined? Where is this undefined? Well, again, it's undefined at x equals 0. Again, I'm looking for division by 0. This doesn't tell me I've got a sharp corner or anything like that. It really doesn't tell me anything like that. Where's the second derivative equal to 0? Well, where is negative 2 over 9x to the 4/3 equal to 0? Just like before, for a fraction to have a 0 value, the numerator has to be 0, but the numerator is negative 2. It's not 0. So there are no solutions here. Again, I can multiply both sides by 9x to the 4/3, and I'd get the absurdity, negative 2 is 0. That would tell me there are no solutions. Okay? So now what I would do would be I would put this number. Really, what comes out of this second derivative analysis is candidates for points of inflection. They're candidates for where the concavity changes. We don't really have a name for that. I would put my number in a table of values, and I would, because I need to know how high to plot this point, and then I would get my y-coordinate by plugging it into the original function. It just happens to be that I get the same important point from the second derivative analysis, 0, 0, that I got from the first derivative analysis. That's a coincidence, okay? It's unique to this problem. You might get different important points from the first and second derivative. Okay? I got the important point 0 from the second derivative analysis down here. Where's the second derivative equal to 0 or undefined? I put that on a number line. I look at my intervals that result. They're going to be exactly the same intervals I had before, only because I got the same numbers I had before. Often the intervals in this second table are different from the first one. So I pick up test value, negative 1. Now I put it in the second derivative because I'm trying to determine concavity. Okay, now this is actually easier than the first derivative because look at this second derivative. Look at this second derivative. Negative 2 over 9 times the cube root of x to the 4th. Do you realize that the cube root of x to the 4th is always going to be positive? Right? Take a real number to the 4th power. It's going to be either 0, but we've ruled that out already because the second derivative is undefined at 0. Any real number to the 4th power is positive. But negative 2/9 is negative. Negative times a positive is negative. So I know the second derivative is always negative. So that means f is concave down. Pick a number in my other interval, 1. Again, the sign of the second derivative is negative. Graph is concave down. So the graph is always concave down. I do not have a point of inflection because the concavity did not change from concave up to concave down or concave down to concave up. But that's an important thing to know. Now let's go back to our original graph and see if we drew it right concerning our concavity. Oh, look. This is concave down, right? Remember, concave down means tangent lines are above the graph. The graph is below tangent lines. Putting the pieces of the puzzle together for the first derivative, this was about the only way we could put our pieces together. And notice we got the shape right without even doing the second derivative analysis. But it's comforting to know that the second derivative analysis confirmed our result. Okay, this is the process, going through these steps that I have on these last two problems, that you'll need to use to graph a function without calculator, using the first and second derivative. Remember, the first derivative tells us if the function goes up or down, the graph goes up or down. The second derivative tells us the shape. Will the tangent lines be above or below?